question on some text.
All right. Can everyone hear me and see the screen?
We hear you fine, and we see your first slide.
Okay, so we're going to talk about APL and K and CoSy and a bunch of stuff in this talk. So first of all, why this talk? I was inspired to give this talk a little bit by a discussion that happened at last month's meeting. I noticed that there's, I think, confusion sometimes with some of Bob's talks on CoSy because folks within the group are missing some context around APL and array languages. And I think that there are some interesting ideas there. Like APL is one of a handful of what I like to think of as the kind of big idea languages, where they are sort of languages that really there's something fundamental to learn from them, even if you don't use them. I would definitely place Forth in that category as well, and maybe Lisp. It's a very small list of languages, and so I feel like that there's a perspective there that's useful to bring. So I kind of wanted to give this talk as my attempt, at least, to bridge some of the gap. And also, quite honestly, I confess that I have taken little peeks at CoSy and tried to follow along, but it is challenging for me as well. And so this was me trying to also educate myself a little bit more. But a lot of the talk, but to be clear, a lot of the talk will actually be focused on APL, just because I think that background is a helpful perspective. So let's talk about APL. So it's created by Ken Iverson, who later won a Turing Award for it. It started out as a Blackboard notation, and I think this is a kind of a key thing to understanding it. This is a language that aspires to be a notation to express ideas in, and so it's meant to be terse because it's meant to be something that could be written by hand. It's meant to be expressive in a way that Blackboard algebra is. And it was only retroactively dubbed a programming language. It was just sort of this thing. And then as IBM started to develop implementations of it as an actual implementation, it acquired this name APL, or a programming language. And it was really motivated by a desire to have a more high-level way to express programs. And high-level is I think, a thing that gets overused. I think there's a tendency, especially in contemporary thinking around object-oriented programming, to sort of treat high-level as meaning you've kind of glued together a bunch of pieces into a bigger and bigger clump until it's somehow high-level. And I think what's meant by high level in this context really is trying to find a different way to reason about things, where you can think about groups of them all at once without thinking about the innards of them. And the ideas in it, even though APL is not as popular as it once was, the ideas from it have suffused into a lot of contemporary array manipulation languages. They even use the terminology that APL coined in many cases, in MATLAB, R, NumPy. It shows up in like TensorFlow. You'll see terminology that sort of, as far as I can tell, originated with APL. So it's definitely, the ideas are out there. I would say that in some ways, the languages that have followed in its wake, so to speak, have picked and choosed and have not always kind of captured all of the ideas. So they're kind of in some ways an imperfect expression of some of those ideas. So what does it look like? It's one of the few languages that is denser than Forth, which is saying something. I've had folks, look at Forth code that I've showed them, and they're like, "What? You can read that? That's crazy." APL takes that one step further, and I think a big part of this is because it has a special character set, which we'll talk about a little bit. It uses infix notation, but it does not use the regular order of operations. It has a strict sort of right binding definition of how an operator is applied, which I think is intended to actually make it more regular in certain ways. It is like Forth, I think, potentially very write-only. It is very easy to come up with a sort of a cryptic passage of APL. And to give you, sort of an initial sense, a piece of APL code that gets trotted out a lot in various variations is this one, which is an implementation of Conway's Game of Life, all in one challenging to comprehend piece of code. It can be used for more complicated things. Here is a giant wall of text that is an implementation of basically APL in APL, or at least the diffens subset of it, in an optimizing compiler with multiple passes. And so it is intending in one sense actually to have a program that you can put up and see it in total, which is I think an interesting direction. So it started at Harvard and then quickly got moved kind of into IBM as Iverson moved into IBM. One of the first implementations was APL 360, which was on the IBM 360 system and had the ability to be multi-user, and so I think this made it appealing in that community, from what I can tell. Because it was something where you were able to have a lot of folks share a system and be able to interact with it. It initially appealed to the finance, insurance, and AI communities because it sort of did, in a world without spreadsheets, a thing that now is used for spreadsheets. It let people play around with numbers, play around with things, even basic things like compound interest, in a way that was interactive, and I think it shares that in common with Forth as well. It's interactive. There are actually, similar to the Jupyter Ace with Forth, there's actually two microcomputers that used it as their built-in language instead of BASIC. One of them is actually a lost artifact, as far as I can tell, on the internet. The Video Brain system had it wasn't the built-in language, but it was the only language offered for it. And it looks like there's the cartridges that have this implementation. There's some guy that may have gotten one on eBay or something, and then refused to have the ROM dumped. So it's a rare artifact if you can find it. The MCM 70, which is all the way back in 1974, is arguably one of the first microcomputers. It's super early days. It borders on being a calculator, but there's a great emulator of it online, and it actually attempts to implement the IBM 360 subset of the language. And so, to give a really simple example, like you can have it put iota 5 and have it count to 5, and it will happily do it. And so it's only got a single LED line display of text, but it's able to do matrix manipulation and a whole bunch of fun stuff, and has that full system there. So it was certainly a thing that people tried to put a bunch of places. And it was called out by John Bacchus, who has this famous Turing lecture on can von Neumann can programming be liberated from the von Neumann style, and what he meant by that was sort of word at a time. Sort of execution of individual operations, and he called it out as sort of something where APL potentially shows the way, because it at least has in its thinking the ability to think about larger constructs without loops, and I think that's a really interesting idea. So let's talk about the character set. The purpose of having the sort of arcane character set is that it's meant to be a substitute for all of the rich symbols that are used in mathematics. Mathematics benefits from the sort of mnemonic terseness of having symbols that you can fill a blackboard with and express ideas with. And it seems like it's a big character set, and in some ways it is, but the actual core character set are really just from 31 characters that aren't in ASCII. And then in the original implementations, because these were done on teletypes with a selectric, they're done with overstrike. So you emit a character, do a backspace, do another character over it. And so this is the APL keyboard, at least in the early IBM systems. And it's not too bad. Like, there's actually only 5 Greek letters in here. There's alpha, omega, epsilon for set membership. There's rho, and then there's iota. So it's not, it sort of has this reputation of having a lot of peculiar symbols, but there's actually a lot of regularity. I've noticed that, for example, in that MCM70 emulator, like the keyboard layout is actually pretty sensible. It's got kind of an interesting correspondence. So it's not as sort of overwhelming and onerous as you would think, given that it's got this rich symbology. But where you get a lot of characters out of it is doing overstrike, and so you can take the jot character and combine it with this upper shoe and get this character, which is used as the comment character, the marker for comments, or a circle combined with a star gives you a circle star that's used for logarithms, and so this sort of combination of two characters giving you symbols ups the symbol count, which obviously has the potential to be very opaque, but I think the intention behind it is that a single symbol can more readily embody an idea that's meant to be applicable to a lot of purposes. We'll talk about why that's important, but you get a big symbol set out of this, and these are at least some of the ones that, at least according to some website, are common. I don't know if I buy that these are all equally common, but there's certainly quite a lot of symbols you can build out of this fairly narrow menu. The language has a notion of both what are called monadic and dyadic constructs. And the idea is that because it's an infix notation, you can either have a symbol sitting in between two values that you're combining, so it's dyadic, or you can have a symbol sitting in front of a set of values. And so on top of it being a lot of symbols, the symbols can mean more than one thing depending on how they're used. If they're used as a prefix, then you get the monadic meaning. If they're used between values, you get the dyadic meaning. So operations like plus, minus, times, and divide are represented with the sort of traditional symbols. But then if they're used as a prefix, they do something slightly different. So you get, for example, reciprocal if you put a divide in front of a number. So like a divide 2 would give you 1/2. And then you have operations like comparison, where you go to the trouble of actually having a greater than or equal to symbol explicitly, which is again in that direction of the sort of specificity of mathematics. You have operations on logical operations, and in APL, zeros and ones are used as Boolean values, and we'll talk about that more later. And then you start to get into richer operations. So you can have things like floor and ceiling. And a thing that I haven't pointed out so far is that the domain that APL operates on is not just the domain of integers or real numbers. It can include complex numbers, and then it also includes not just matrices, but arrays in arbitrarily large dimensions. And so another idea that you'll see suffusing array languages is that you want to be able to talk about our multidimensional things using the same operations that you would use with single values. And that the intention is that this is means that the operations have sort of meanings that you can generalize. You can see something used in a single value context or in a two-dimensional context that then equally applies to a three-dimensional context or an n-dimensional context. So there are symbols explicitly for things like floor and ceiling, but they're also reused for minimum and maximum, or magnitude. An interesting choice is that the star operation, which is in a lot of languages with a less rich character set used for multiplication, is instead used for exponentiation in APL. There's a natural log operation. The one kind of weirdball one actually is the circle, which is used for either pi times the value, or it's a kind of a grab bag of trigonometry operations. Depending on the number that you pass into it, you get sine or cosine or tangent. So rather than sort of warranting their own symbol, they share one, and unfortunately you get these kind of cryptic numbers. This is something that's a little bit odd with the aesthetic of it, but it is what it is. And then, but there's symmetry to it nonetheless. You get if you have a negative value, you get the inverse of that operation. And for example, this one has no inverse, so it's missing a value. There are operations ones that you'll see a lot, and there's, as I mentioned, a handful of Greek letters, but they're used for kind of really important purposes. So the iota operation it produces when you pass it in, when you use it monadically, will produce a series of values. So you remember before in that emulator, I passed in iota 5, and that means the one-dimensional array of values going from 1 to 5. There is a whole subtopic. There's actually a question of where you want to index from, but like classical APL, the default is indexing from 1. We'll talk about that in a moment. And then because you're dealing with things in multiple dimensions, you need a way to both examine their dimensionality and get the array of dimensions. How big is it in each X, Y, Z, W, whatever, however many dimensions you have. And then you also want to be able to reshape things. You want to be able to take an array and kind of bend it and twist it and reimagine it in different shapes. You want to be able to glue things together. The bracket operation is a little bit of an oddball. It actually has a little bit of a grammar to it because it's parsed as a kind of like an array notation in conventional languages. But where in a conventional language, when you have a bracket, you're assuming that you're going to pass in a single value and index into it. The bracket operation APL is much richer. You're passing in potentially multiple values, and then as a consequence, getting multiple values out. So big symbology. You've got operations for finding, not sorting an array, but rather finding the indexing of that array that would give you the sort order or give you the sort order in reverse. There's composition where you're, compress, where you're taking I'm going to describe it wrong, so I'm going to let me skip that one. And this is the challenge, right? There's a rich symbology here. It's large, but it's not sort of infinitely large. There are a particular set of operations that you kind of need to have wired in your head to be able to parse this thing. There's operations to monadically reverse something along either the last dimension or the first dimension of however many dimensions are in the array, or if you pass in an initial value and it's dyadic, you get you shift it by some number of positions. So you're sort of sliding the array, looping the array around, or and there's visual. You're getting visual things out of the representation. So like this, vertical bar is telling you that you're doing it on the first dimension. The last dimension of the thing. Here you're doing it on the first dimension, and then this slanted one, you're doing a transpose, you're flipping it. There's membership tests, there's the ability to encode and decode in different bases. Matrix inverse is interesting. Remember we were talking about composition before. You've got the divide operation inside of a box to highlight that it's sort of has a correspondence to divide alone as a monadic operation is a numerical inverse. Well, this is the matrix inverse. And there's a whole elaborate thing with axes that I'm not going to talk about. And then there are operators that act on these basic symbols, and you can take an operation like a plus, for example, and combine it using a slash to do a reduction. So, for example, then to add up all of the values in sequence. And you can do the same thing. This slash with a dash does the same thing, but along the first axis. And there's a whole debate about whether the first or the last axis is sort of the ideal thing. There's two really powerful operations. There's the ability to do a very general inner product. So where in a language like MATLAB, you'll have something like an inner product that assumes a conventional matrix product. Here you've got arbitrary dimensions. And you pass in the value, you pass in the operation that you want to use to combine elements from the first and last dimension of each of the values that you're multiplying, and then when you combine them and collapse them together, you have a separate operation. So for a conventional matrix multiply, you'd have a multiply passed in here followed by an add. You have an outer product where you get sort of all the combinations back and forth between the two along each dimension. As I mentioned before, there's no, the conventional order of operations is not respected, so you don't get what you would expect with conventional mathematics the multiply here, the second, it will happily do the rightmost operation first, and then combine it with the secondmost. So in Iverson's own writings on this, he flags APL's goal as being that it's a notation as a tool of thought, and I think this is key to understanding this whole domain, because really what's going on here is that you're saying what would be a good notation to talk about complicated ideas, to talk about computing. And so he calls out in his paper on this topic sort of 5 ideas: that it should be easy to express interesting problems in the domain, that you should have suggestivity, which is a very interesting idea. It's something that you don't see in a lot of programming languages, that sort of similar to algebra, you're going to have how you've represented it suggest other ideas, and then the ability to sort of hide detail. You want economy to it. And then you want to be able to do formal proofs. So let's talk about each of these in a little more detail. So here's a really, really simple example that's from the paper. So as we mentioned before, you can do iota 5, and you'll get the array of numbers from 1 to 5. Well, this operation, the slash, is called a scan. And what it does is it takes the operator that you've passed into it, and it applies it cumulatively. So you're doing this operation with the first value and the second, and that becomes your new second value, and then you do the result of that, and that's your third value, and so on. And so you're incrementally adding things up. And so imagine that you've got a triangular layout like this, and you want to count how many total values do you have. Well, you get that with this operation. You take this range of these 5 values, and then you're summing them up one by one. So you have 1 item, now you have 3 up here, now you have 6, now you have 10, now you have 15. And notice that we did this, construction of figuring this out and figuring out this list of values without loops. We didn't have to think of it in terms of loops. We were able to just express it a little bit like summation notation. Similarly here, imagine this is the reshape operation. It's confusingly in Greek, remember the symbol that looks like a P is actually a rho, R sound, so hence it's a reshape. And you can take a pair of numbers 3 and 4 and say, well, I want to reshape this 5 into an array that's 3 by 4. And you can do that in a number of different ways. Suggestivity, I think, is one of the more interesting ones. It's basically the idea that if you, in algebra, when you see something on the board, you can infer things from your intuition about how to think about it. And so obviously there's basic things where your mathematical knowledge translates back and forth. But when you, for example, if you've got the way in my head I think of this is this is like a summation sign, right? This is like the capital sigma. If you have the summation of taking a single number and reshaping another single number into it, where you've got m n's laid out, then the summation of that is the same thing as multiplying, right? Because you're summing m n's. And similarly, if you're multiplying, this would be like a capital pi, if you happen to know that notation in conventional math. If you're multiplying m n's, then you're getting n to the m power. And so that correspondence is a very direct kind of mathematical correspondence. And similarly, the same thing happens with the scan operations. If you lay out each of the values as you gradually sum values, it's the same thing as if you were taking n and multiplying it by the sum of multiple by the values that you've counted out, and multiplying each of them by n, or the same thing if you multiply. And so you're able to do these transformations and see them visually, similar to conventional mathematics. Ability to subordinate detail, sort of 2 ways that the paper takes this. I don't know that I buy it has that great of an ability to subordinate detail, and maybe we'll talk about that later, but this is at least a thing Iverson asserts. Certainly you can do things similar to fourth, where you can define the left arrow is a way to set a value, so you can give a name to a value, you can do an operation and store that into a value. And then you're also able to subordinate detail in the sense that, you can talk about the numbers from 1 to 5. This is the reverse operation, right? It'll reverse things. So if you talk about the reverse of 1 to 5, you now have this very terse thing that you can talk about, right? And the comma operation joins together two things. It concatenates them, I believe is the term. And so if you talk about taking the numbers from 1 to 5 and the reverse of the numbers from 1 to 5 and combining and concatenating them, this is what you get. And this is a very visual, very direct way of representing that. If you had a function that said reverse and you had to give it a name and you had to have a loop and like all of that detail would be lost. And so the idea is to be able to see that in one sort of terse, direct piece of code. It's got economy is another idea, which is that it has a large number of ideas packed into a small vocabulary. There are maybe I would say 3 dozen certainly commonly used APL operations, and they can do a ton of different things. There's just so many ways you can combine them, particularly as they all operate on multidimensional things. And despite this, they all kind of have the same behavior. They have the same precedence. You can kind of assume that they will, if you kind of understand what they'll do in 2 dimensions, that you can infer what they'll do in 3 dimensions. And so you get a lot out of a little with it. And then here's another one I'll go through because the way it's shown in the book is kind of fascinating. So amenability to formal proofs, which is certainly not something I think in the fourth community we've plugged into, but let me just go through this exercise. So here's a lemma that gets used in the proof in a moment. So this is not really a proof of this lemma, but basically it's a visual proof of it. So imagine that you've got 1 block, 2 block, 3 block, 4 block, which you could represent as these numbers 1, 2, 3, 4, 5. Well, if you had the kind of the reverse of that, the 5, 4, 3, 2, 1, and you add them up, well, you'll obviously get 6 blocks in each row. So you get 5 6s. Well, remember that we can represent that with this row value. So we can say, n reshaped of n plus 1, right? If n is 5 reshapes of 6 gives you 5 6s. Well, we can make the general statement that if you take the sum of 1 through n and the reverse of the sum of 1 through n, you will get n plus 1s, right? So keep that lemma in mind. And then what you can use this to do is to, for example, prove Gauss's formula. Gauss's formula is a statement, remember, about the summation of the numbers from 1 to n. And what you do to do this very formally, right, is read this again and remember as a sigma summation. So the sum of I from 1 to n is equal to the reverse of the sum of I from 1 to n. You can infer that based on associativity and commutativity. So, and then if you combine those two things, you add them up, the sum of 1 to n and the reverse of the sum of 1 to n, and divide by 2, you're going to still get the same value because x plus x divided by 2 is the same as it's just x. And then you can use your mathematical intuition to say, well, if I've got a summation, 2 summations, I can pull of 2 different values, I can pull that summation to the outside. So now I can talk about the summation of, and really this is leaning on associativity and commutativity. And so now you've got the sum of 1 to n plus the reverse of the sum of 1 to n, all divided by 2. And then we can apply that lemma that we just proved to transform this into n-shaped n instances of n plus 1, and the summation of that divided by 2. And then we can use this is just the definition of multiplication, right? If you have the sum of n plus 1s, that's the same thing as n plus 1 times n. And so there we've shown Gauss's law. And so notice we're proving a mathematical idea here, but we're using this notation that thinks of it in terms of that is also simultaneously a programming notation. APL also gives you the ability to define your own operators. Although a surprising thing with APL is how sort of in conventional usage how rarely this is used. I think it's in service of the ability to be able to see those visual patterns. But there's an old notation to do this where you use this delta symbol, and then you specify the operation, and you can give it named parameters. You may have a comment, and then you do a calculation, and then you can apply it later. You can say 3 Pythagorean 4, and it'll do 3 squared plus 3. Notice, read this as squared, so a squared plus b squared, and then notice that this little sequence, right? You're doing a divide by 2 is a 1/2, right? Because it's a monadic operation. So this is raising to the 1/2 power, or square rooting. So this little sequence means square root. You can have local variables, but you have to specify them, because otherwise that you'll actually get global variables, which is just a symptom of it was very common to have global variables at the time that this language developed. Later, the language developed this new approach called diffins, which adds this curly braces, and this is used in later APLs. And here you use alpha and omega to mean the first and the last parameter of an operator. And so then you can kind of very tersely represent the same formula that we had here, all in one glorious line where you're talking about the square of the first parameter and the last parameter square rooted. And this got bolted into the language, but and it also has the ability to do things. There's a syntax for doing recursion here, so you can do a factorial by saying, well, if omega is 0, then you get a 1. Otherwise, take omega times the recursion of calling this operation itself with w minus 1. So you sort of do a recursive factorial. When this notation developed, originally it was implemented in APL. And again, here's one of those terse walls of text that I don't purport to be able to parse, that implements was one of the first implementations of diffins in conventional APL to be able to sort of glue it in. So this language had its heyday, especially I think when it had IBM as its sort of corporate sponsor. But it spawned a bunch of children, and one of them was J. I think there was a number of ideas in J. J attempts to address the concern that you used to get back in the day with this language was all the symbols makes it very challenging in a world that's all filled with ASCII, and so it tried to come up with an ASCII notation for all of this. There's a greater emphasis on the sort of point-free style where you have everything kind of bereft of particular variable names and operators. And then there's, which is very similar to Forth, by the way. And then I said that, oh, that's weird. That slide is redundant. And then there's a little bit of a renaming of it. And it also is sort of famous because Arthur Whitney enters the picture and you start getting these very terse implementations. He actually has it, there's this famous implementation where it's done in C. This is the whole thing in C, and amazingly, apparently you can write APL in virtually any language because this is super, super terse. It tries to create a correspondence with symbols, and so you'll notice it takes these already opaque symbols and now substitutes them for multiple characters in ASCII. And as much as I can just barely keep these APL symbols in my head, oh my word, these J ones in particular are really challenging. I mean, there are patterns to them, right? Like there's a tendency to use colon and period as a sort of a modifier, but it's a lot. And then you get K, which is Arthur Whitney's creation, and it's ASCII, but it focuses on really just picking the most important operators, trying to give them single symbols. And he's gone through many iterations of this. It's actually, K is not one language. It's got this sort of a KX. There's K1, 2, 3, 4, I think maybe up to 9 of multiple sort of incompatible generations where he's sort of futzing with what are the core operations here? Do you really need quite so many symbols? And he also, takes an interesting pivot. He starts to emphasize instead of just thinking about arrays, thinking about functions as kind of the core operation and more function manipulation, and also thinking of lists rather than thinking of multi-dimensional arrays. And so the correspondence here is, you'll notice there's not every APL symbol, but rather there's a kind of a narrow subset, and you really do get a pretty small mapping. He still uses monadic and dyadic things, although they're nouns and verbs and so on. But you're really down to a very small subset of them, and you kind of make do without the others. Some of the ones like the circle operations actually get stuffed away under names, because in practice you don't actually use sines and cosines much unless it sort of is in your domain. There's a whole bunch of others that I'm missing that are kind of stuffed away in the annex, so to speak. But the core operations are just these few. And then, so anyways, that's kind of the genealogy. We'll talk about CoSy in a second. But so polymorphism, there's a thing that is common in all of these is that you're really trying to have the operations in this language deal with a broad domain. And so you get binary numbers, integers, reals, complexes, and then matrices and multidimensional arrays, and they're all kind of one thing. But for focusing just on single values, right, you have some operations that implicitly assume that their input will be binary, and this actually allows implementations of the language to be quite performant, because what you can do is, if you know that a particular array is filled only with binary values, you can optimize this and actually bit pack it and do all the things, and you can only at the granularity of the moment when you're sort of mixing types together do you actually have to pay the cost of up-leveling things. And so this, so many operations preserve the type of the operation. I meant that to be a multiplication, but failed to do it correctly. And then there are some that transition types. So if you do a division, now you have the risk of getting, with an integer, now you might get a real number. If you're doing comparisons, now you might go back from floating into binary. But if you're doing a power operation, now maybe you'll get a complex number if you do a negative square root. There's boxed values. So you can have mixed types, but you only have to pay for it sort of if you use it. And a common pattern you'll see in array languages, particularly if they're trying to be very efficient, they will try to have all of the kind of the things that are mixed types be up at the top level, and then deeper down they'll try to have uniform types, because the implementation can make that very efficient, even in an interpreter. There's a whole fun subtopic around how you deal with representing multiple dimensions. If you do that, CoSy, which we'll talk about in a minute, similar to K, collapses this and it focuses on sort of lists of lists and only the one dimension directly. But if you do this, there's a bunch of philosophical questions that come up. Is a single value the same thing as a multi-dimensional array that has is one dimension in three dimensions and so on? There's been some transitions in terms of how this is approached, and all of this is in service of letting you kind of reason about these things in groups and have operations behave uniformly. It's almost a little bit reminiscent of the feedback I got on haiku forth, where people care very much about making sure that the operations are kind of mathematically beautiful and have the right behavior that you would assume. But let's see. So let's talk about CoSy. So CoSy, created by our friend Bob Armstrong, is an attempt to translate K's idioms to Forth. It's built on top of a Forth implementation called Riva Forth, and it focuses on having typed 1D arrays, so integer, character, float, and box types. And similar to K, the thinking is that if you have the right set of operations, you can cope with these lists of lists in cases where you want them to be multidimensional and have that kind of naturally fall out, rather than need to have that be something directly represented in the language. And this hopefully is a simplification. You hopefully end up with fewer total operators. And the vocabulary, I would say, is there's certainly K-isms in there, but it's also K is a fixed target, and is not a fixed target. And so there's a mix of different generations of what the operations are. There's definitely some APL-isms in there as well. Reva Forth was created by Ron Aaron. It's case sensitive. That was a gotcha that it took me a little bit of time to realize, actually, weirdly enough, that it's like, why is this not working? And I suddenly realized, oh, it's case sensitive. It has, rather than using curly braces as a for locals, as some implementations do, it actually uses it for inline no-name functions. And so this is actually very happy coincidence, because it ends up mirroring APL's diffins. It's an x86 forth. There's a lot of stuff that gets implemented directly in x86 assembly, and it has some facilities for sort of a GUI or a TUI built into it. Another gotcha that you'll find if you're looking at the CoSy code base, Bob has these interesting shortcuts for stack manipulation, where you'll visually describe the stack effect of a transformation by showing, if you had A, B, C, D, go into the value, what happens to it. And he's got a rich set of these and uses them throughout the implementation. So this can actually is an interesting convention. Like I think it has the potential to take operations that I have to sort of think about. And there's an interesting correlation here, weirdly, to this is actually kind of oddly the converse of a thing that APL does a lot, which is APL talks about what are called idioms, where you'll have a sequence of words where you sort of you intuitively learn to know what that sequence of words means. Here, Bob's given them names, but maybe arguably in a way to make them more idiomatic, strangely. So let's talk about syntax with CoSy. So CoSy can do these kinds of array operations that all of these array languages do. I've got a typo here. There should be a space after this. This is so he's got a way to specify a list of integers that you can explicitly specify, a list of floats, a list of strings, or you can have single values. And a key thing here is that CoSy has a distinction between, it is still done in forth, and so you have the forth stack there and all of its behaviors. But when you want to do these array operations, you need them to be one of these boxed types, and so there's a careful transition that has to happen. You have to either convert a group of them, or you have to explicitly convert them singly, or there are a number of words, and you'll see this convention throughout, where an underscore means take something out of the forth stack and transition it implicitly into these typed things. The other thing to bear in mind is that these are reference counted. So there's some care that has to be taken so that when you're manipulating a value, you need to make sure that you're not just, for example, if you took this value and you just duped it, you're potentially going to have the wrong reference count. So you got to be a little bit careful with that. There's a syntax for a single word string. And then per type, there are these rich operations that, if you think back to those APL operations, they're the same thing. They're this arbitrary dimension, dyadic add and subtract and multiply. However, there are places where Bob has gone through and made them generalized for types, and there's some places where it seems like he hasn't, or he hasn't completely. So for example, you'll see a whole bunch of these with I as a suffix that do this for the integers. There's a similar set for the floats. And then there are a bunch of words that are general. And so, for example, a useful one if you're dealing with the command line is list, which will print not just a list, it'll print any of these boxed values. You can do iota, which is, remember that iota symbol in APL, and underscore iota will take it off of the fourth stack. There's catenates with integers, or generalized ones with lists. There's the monadic operations. There is reduction operations. So you can do a plus slash, just like what we saw in APL, or you can do a generic version of that does it with an arbitrary. The dot here is meant to imply that you can pass in an arbitrary function. There are some of them that are named, some that would have been, symbolic ones like that circle with a line through it in CoSy are given names, which I think is a little bit more forthy. And the other thing to call out here is that where APL has you have to worry very deeply about the sort of monadic and dyadic distinction, because that influences how it's parsed. In CoSy, you're explicit about when you're doing a monadic or a dyadic operation, because the left and the what would be the left and the right side in an infix notation is sitting there on the stack. So you're thinking in terms of a stack. And then so let's I'm going to do a demo of a thing in a minute with CoSy, but let's talk about array languages in Forth in general. So there's some commonalities. Both try to be tacit, point-free style. What I mean by that is that you have a series of operations that you do one by one, and you don't name your variables, or at least you don't if you're not using something like locals. And this is a powerful thing, because it lets you this is, I think, why Forth can be refactored, because you can take a sequence of words and you can say, oh, I can grab that, I can give that a name. I think it's used for a slightly different purpose in array languages, at least at least with APLs. There's also an element of identifying common idioms. Actually, sorry, I'm out of order on the slide. Both are notorious for being write-only. I think that they suffer from some of the same sort of perils. They strive to have a minimal core. I think that it's interesting that both of them are languages that somebody contemplated, stuffing on a microcomputer as the only built-in language. Forth, this is phrased weirdly, Forth also has idioms. We have sequences of words that we recognize as Forth programmers that are, we recognize them as a whole word, even though we sort of say them as separate words. But there are some differences. I think that array languages more deeply favor idioms. They tend to, you tend to need to learn to recognize these sequences of operations, because they're very general, and you could, if they apply to an array of integers, they might also apply to a multi-dimensional set of arrays of floating points or strings or something. And the array languages favor memory safety, although I guess CoSy does not quite have memory safety. It is very much a low-level language in that sense. I would say that array languages have an unclear sort of relationship with how they deal with state. I feel like that was sort of the thing that Bacchus calls out as kind of why he doesn't point at APL as the one grand solution, but as sort of a step in the right direction. It sort of got the right ideas of how do you deal with programs and think higher level than a loop, but it doesn't necessarily figure out state. And then certainly array languages, I think, have a greater emphasis on mapping the problem to the language rather than the reverse. Where I would say that Forth tends to, you find a domain-specific language to map your problem to, and you don't try to sort of shoehorn it into a fixed set of operations. So sort of, again, even more zooming out, like what is there to learn here? There's this quote from Alan Perlis that gets trotted out of, it's better to have 100 functions operate on one data structure than to have 10 functions operate on 10 data structures. And this is definitely, this was, I think, in reference to Lisp and Lisp thinking, but I think that in some ways, I do agree with the assertion that APLs and array languages embody this even better, this hope that you could have one data type that is sort of general in the same way that when you think about mathematical values, you have kind of one data type. I think this goal of finding a notation that is elegant, that is lets you express big ideas in a small number of words is a powerful idea. I think that's kind of what mathematics is about. Einstein called out the inventor of tensor calculus, which he used in proving relativity, because he felt like this made the difference. This made, being able to have a notation that you can put on a blackboard, that you can express your ideas in, and sort of fit it all on your screen and fit it all in your head is important. And I think that's kind of the nub of like what I see, the value that I see in APLs, and the value that I can see in CoSy is that there's this desire to squeeze, fit that whole idea just on a pithy line, and Forth tries to do that, I think, as well. And I think there's also an element of it's alien, it's a little bit alien, and I think Forth suffers from this too. But if it took a long time to get to the mathematical notation that we have. It wasn't a it wasn't a 10-year thing. It was hundreds of year thing. And if you think about like Newton, he proved his theories not using calculus because the people of his day didn't think that you could meaningfully express things in the kinds of notation that he was newly inventing. It took a long time for us to adopt notations around algebra and calculus, and so he did geometric proofs. And so I think that just because some of these notations are challenging doesn't necessarily mean that they're the wrong direction. I think it just means that we have to shake out what works, what doesn't, what has good idioms, what is mnemonic, and figure it out. So what can we learn here? I think that maybe we could be using a more powerful base with Forth. I think that it's very fascinating to me that these array languages have been put in microcomputers, that you can squeeze them into a very small amount of space. Implementations of K and even CoSy are quite small in the scheme of things. And Forth, we try to go super, super amenable, and we're down at the level of individual loads and stores, kind of that von Neumann style. Maybe that's not the right base. Maybe our core operations should be a little higher level. There's something to that. If we have the right set of powerful operators, maybe you don't need as many arguments, and that's actually really good for a stack-based thing. If one of the things people struggle with in Forth is too many things on a stack, and having powerful operations that deal with whole multi-dimensional things is a good way to not need as many items on the stack. It is interesting, this perspective that domain-specific languages could be a distraction. That if you come up with a unique notation for everything, now you're not necessarily able to spot the common patterns. Part of why we get value in mathematics from having a common notation for things is that we're able to look at a pattern and recognize it and apply it in multiple places. And people that use APLs claim to be able to do this in the same way. They're able to see a correspondence between a parser and some other operation that they see in some other wildly different domain. And we miss out on that by sort of boxing things up in domain-specific languages. Maybe we should use more symbols. It is kind of powerful to have them. I don't know if I can quite keep that many in my head, but I think that there is something to it. There's something I think where I struggle with CoSy is a syntax with K, certainly. I do find the rich symbols in APL appealing because I find them easier to remember what they mean because they are pictographic in a useful way. Maybe we should find more idioms in Forth. I think there are patterns that there's some discussion in thinking Forth about the trade-off between giving something a new name versus using it idiomatically, and Chuck even calls some of this out. And I think that there are places where we don't talk about the stack manipulation idioms in that way. We think about it as we tend to emphasize, just refactor it, give it a name. But there are kind of the noise words, so to speak, in Forth that they really are kind of idiomatic short expressions that tell you how to do a certain operation. I'm tempted to come back. So recognizers, which I've talked about previously, which is this new idea in some of the current Forth standards bodies, where you're able to add new types of constants or new types of automatically recognized things. You could probably make Bob's stack manipulation operations something that are automatically generated on the fly by the system using recognizers. So maybe that would be cool. This whole exploration has made me wonder a little bit about infix. One of the advantages of infix is that it's easier to see patterns that let you refactor things positionally with it. I'm describing that badly. And maybe that's something that we could add. I've got sort of an undigested thought about could recognizers be used to introduce infix in a more very limited way to Forth. Possibilities there. Certainly, I think this aspiration of avoiding loops and conditionals. If you in thinking Forth, there's a long discussion about trying to avoid conditionals if you can calculate things rather than have those ifs. And I think APL does an admirable job of avoiding it, and going a step further and avoiding loops is an interesting concept. Is math kind of the way to have higher level things? And then what suggestivity does fourth have? If we look at a fourth program, does it actually let you recognize how to make it better, how to make it interesting? So one last little digression, and I apologize if I've gone a little long here. I got the notion, and this has been a thing that Bob has asked about occasionally. Wouldn't it be cool to have CoSy in the web? And so I thought I initially tried to port CoSy to run on top of micro eForth and quickly gave up because it's got so many Riva isms in it, which is a challenge. So I said, well, let me try the kind of the more roundabout road, let's say. So there's a big stack of tools. There's a thing called Wine that is a Windows emulator because CoSy runs predominantly on Windows. And it's a set of folks created an emulator to let you run Windows programs in Linux. And there is yet another project called Boxed Wine that lets you take Wine and run it on top of an emulated Linux emulator. So it's boxed in the sense that you're taking Wine and then running it inside of another emulator. And then there is a tool from a fellow I actually know from work, Ilan Zakai, who's written this great tool, Emscripten, that lets you compile C and C++ code to ASM.js or now WebAssembly so that you can run it on the web. And Boxed Wine can be built with Emscripten. And so taking all of these things together and using WebAssembly, which lets you run low-level code on the web, you can take CoSy and run it on Wine, running on Boxed Wine, running on WebAssembly. And I have this working. It is very slow because of all these layers of emulation. So I will take that with a grain of salt. I don't know if this is the right solution. There's at least one glitch that I've seen with this around how it deals with window handling. I think what's happening is that it's being emulated so slowly that it actually throws off some of Wine's emulation of the screen. And you'll see it down here. You can see that the console, it's booting up very slowly in the console. And once it gets done with that, it will load, and it's got Windows here emulated, and it's still loading, still loading, still loading. Come on. Very patient. Okay, and so here is the environment that you've all seen Bob put up. This runs locally on your system through all of this layers of emulation. And so you can do things here like that same example we talked about before. If I do 5_iota, and then I do F6, what that will do is execute that code, and it's slow. Now CoSy is zero-based, and there's a whole debate in the APL community around similar to the programming language community had kind of moved on from one-based indexing. It's funny because in some ways a lot of the nice examples of APL work more nicely when they're one index based, but I do think that in general the industry's move to zero-based indexing is probably the right call. So you can do an operation like that, and for example, say I wanted to sum those up, I can do +/ and CoSy will happily, oops, I gotta hit the right button. Yeah, it will calculate the sum of those numbers. Let's see, I can do a scan instead, so I can get those numbers incrementally summed up in a scan. And I won't belabor this because I will confess that my agility with CoSy is limited. I'll also mention, if you're interested in poking around with APL, there is a marvelous implementation of it. This one's snappier, quite envious of, that has a great tutorial for APL, and you can do similar things. There's a guide to, you can type these characters readily, so you can do the 5 add, you can go back and do the summation, you can go back and do the scan, things like that. And with that, I will flip back and take questions. Shocked and stunned silence.
Yeah, with all the everybody stunned, I'll tell you that is fantastic. And actually, in a sense, I could have just taken all of your slides and done some annotation of them. And because I've that's the world that I've come from. Um, but yeah, if anybody has any questions, let me, before going and doing a little bit of additional stuff. But uh, I guess
I guess
maybe
I had one question, and I don't know if it fits in with this or not at all. I don't know if everybody ever saw the mother of all demo, not the mother of all demos, but I think Engelbart or whatever. He did something which was doing, for example, a royal tree of demonstration of who's related to who, and this kind of stuff. And I don't know if, for example, something like that could be done in in something like this.
So there,
I
so there is an interesting kind of fairly recent a bunch of folks in the APL community have been really thinking hard about tree representations, and there's a whole body of like how you think about trees as represented in various types of kind of scans over arrays that use multi-dimensional arrays. Certainly with languages like K, you can represent the tree directly, and there are operations you can do that way. So I think there's sort of two different schools. I think the APL folks that have been playing around it recently, there's like, I'm forgetting the name of the fellow that I think his name is on one of the slides. He's the guy that created that codiffins thing. He's put a bunch of energy into developing not only doing APL, but doing APL that runs on the GPU. So I think the reason he's trying to do trees with arrays is because he's specifically trying to take advantage of the GPU for computation. So it's important that it be uniform. So there's a whole like body of like, how do you do various compiler tree manipulations, thinking of them as various types of arrays. But yeah, and I don't know, Bob, if you can speak to the broader.
Yeah, I might as well go and make some comments, starting from the beginning with John Bacchus going and his Turing lecture. Oh, and by the way, every year I keep pressing one way or another. Chuck Moore is the most deserving of a Turing Award. That it shows in a sense the rebel nature of Forth. That he's it just is it does not reflect well on ACM. That like Jeffrey Hinton now has gotten a Turing Award, but not Chuck. This is just really. But one of the things that to Bacchus in 78, I believe it was, or 77, he mentioned this Ken Iverson overcoming this von Neumann bottleneck of essentially scalar thought, which virtually all the standard languages think of doing things on one item at a time, as opposed to coming from Iverson generalized the notation of matrix algebra. He was coming from matrices and tensors and all these rectangular, multidimensional rectangular data structures. And so that's where it came from. And I learned APL when I was realizing that I had to learn multidimensional geometry and its algebra in order to understand things like pattern recognition. And this was in the 70s and so forth. And but Bacchus I mean, I think that Iverson may have gotten his Turing because of Bacchus's talking about him the year before. And
I got that impression too, actually, from some of the material, and I think there was this interesting call out, and Bacchus was known for his work on Fortran and so on, but I think and the odd thing then is Bacchus goes and spends the rest of his career kind of focused on this language FP and some of its descendants, and it feels like it sort of never found the answer to his quest exactly. Like it's an interesting history there.
But,
I do feel like it's a kind of an unsolved problem in the sense that I do agree with his sense that APL shows the way and these array languages show the way, but I also am not sure it shows the whole way. It's sort of there.
The point that I wanted to make, because APL, again, coming from this and generalizing in many ways, like the f dot g as opposed to plus dot times. I mean, an inner product was old plus dot times, and Iverson said, well, hell, throw in f function, apply g item-wise to these two data structures, to these two arrays, and then do the f across them. And that gives you, I mean, literally in CoSy, that's what it is, and in K. But the point that Bacchus made is that instead of having these rectangular sets, you could just have lists of lists. And you see the evolution from the APLs, where essentially all the operations started on the, if you will, the innermost dimension, the last dimension. You see now they all have operators to act on the first dimension.
Yeah, all of these operations that have like the slash line, and they've incrementally realized the first dimension is the dimension you want to operate on.
They're not directly symbols that go and do that. They've added, symbols to the language to go and mean, well, count, for instance. They've got one now, count. And it's a rather, in any case, that came in like the 80s, and then you started having the nested arrays and debates about how that should be done. I guess that mainly was going in the 80s and so forth. But then again, Arthur essentially went to what Bacchus had pointed out in the first place. All you need is lists of lists of lists, and you have. And when APL split, there was the Iverson J off into J, which was more mathy. And again, as you point out, it is really indecipherable because it's got these multi-characters things, but it does not have, again, one of Chuck Moore's, simple brilliances. I mean, I think one of the things important is simple brilliances, and having white space to go and delimit your words.
I will say that I confess that even though CoSy avoids some of that, it still is to me, like, because it ends up being multi-character, I struggle with the suffixes and that's challenge for comprehensibility. I think that there is some peculiar merit in the richer symbology, but I think you're right. There's too many of them that were the wrong way also. So,
absolutely.
For those who didn't notice it, we're with Bob's portion of the program. So it should be interesting for Brad to divide these videos into which is one. It may just turn out to be one long, excessively interesting.
Yeah, actually,
were there questions directed at my talk before we make that transition, and then we can,
I have one.
Hey, John, it's good to see you, by the way.
Yeah, I decided, even though my hair is okay. The question I have is, they started out with these little rotating balls with an alternate character set, and they would, imprint things twice. I guess Bob is using this thing where you do __ AA to show that you've duplicated the stack, which I sort of like. So the real problem when you overstrike characters is everything becomes one character. And to me, one of the problems is when you start a language like this, you've got to learn the character set before you can start programming. And you went through in your slides showing the two versions of and the whole business like that. So to me, what's your preference? When I looked at the overstrike thing, the rotate left and the rotate right made no sense to me at all. As an SVG programmer, I would have a rotating arrow to the left and a rotating arrow to the right and two underscores to show it applies to the stack. So look at the Chinese character set, which might be thousands of characters, but they're very mnemonic. They represent something physical. And from the age of 3, Chinese kids learn them. And of course, Western people like us are out of luck, right? So I feel that there's a big discussion that can be made for what do the characters look like and what do they mean? And I think Bob did the right thing with the underscore AA. I'm not worried about character count. We've got large screens.
I think, yeah, no, it's a fair point. Like, it's definitely that character set is born out of the constraint of what they could do with the selector type ball. And I had a back and forth email exchange. Like, I'm surprised that the alpha and the omega made it into that character set, because in original APL they weren't used, and then later they show up. So it's almost like they built the symbology out of what that character set was the constraint. But you're right, it's very arbitrary. If you're trying to come up with a better set of symbols, maybe that wouldn't be the one. I do think in terms of the learning of the character set, I think one of the various things I read on this topic that calls out, which I think is an interesting point, is that the way that you the way that at least I think Iverson intended these symbols to be taken is not to sort of swallow them all in one lump and then the language. He viewed them as something where, imagine you were doing a math lecture and you were sort of learning things one by one. You'd gradually introduce one symbol as you start using that symbol in your discussion. And so they were sort of the way to cope with the volume of the symbols is that you're kind of introducing them one by one, kind of as you go in whatever discussion. Now, I don't know how you keep them all in your head if you then are using them in daily life, but so.
It's if my wife's a teacher. It's as if instead of the first grade class where you say, here's a bear or here's a squirrel, and they say hi, you give them some novel or Shakespeare and say, now we're going to learn language. So I agree. The Blackboard model where you start with a small set and expand from there, I understand how that evolved. Yeah. Okay, thank you, Brad. I'm done.
So, Brad, what was the motivation for this?
Little bit of I've seen a number of Bob's talks. I think produce confusion when he's talked about sort of APL-isms in the language, and it was my attempt to both refamiliarize myself, but also kind of bridge that gap. I also do feel like there is something here. Like APL is one of the sort of special languages that has this, and APL in the family of languages around it, of thinking about programs in a way that is very different. And so I think it was sort of that contrast of wanting to ask the question of, like, Bob has been trying for many years to say, well, here is this aspect of APL or array languages that could potently be brought into forth, and I kind of wanted to have a look of my own and say, well, what is it I'm seeing here, and what resonates and what doesn't. So.
Well, one thing, Brad, I think your overview of APL, I'm going to definitely pass it back to a lot of the APL community, because it really, in many ways, is very. I mean, it very good overview of a great deal of it. I mean, I got a few quibbles and elaborations.
I'm sure I got a few things wrong in there, Bob. I readily admit I'm not an expert APLer by any, or not even. I'm not even a novice APLer by any stretch. So.
It's Roger Huey, not who recently died, who went with Ken and created J. And John Scholes actually is the guy who originally did, and still is, I think, one of the best demos of APL thinking, I'd put it that way, in his Game of Life, which has now got well over 250,000 views and so forth. And he's the one who really created defunds and so forth, which in a sense is the way things should have been done from the beginning. You know? But I don't know. It really is interesting to see. I can get into